humans are changing the climate system has almost no precedent in the entire record of Earth. Melting ice sheets, acidifying oceans, shifting rainfall, rising sea levels. Both climate change and, of course, its impacts are accelerating. Heat waves, marine heat waves, fire, storms, droughts, heavy rainfall, we know all that. But this third one is really important. For the first time, the IPCC really emphasized catastrophic events, tipping points that I'll be spending most of my time talking about. Collapse of major ice sheets, rapid temperature spikes, and so on, cannot be ruled out and should be part of risk assessment. This was a big step forward, I think, in getting tipping points and extreme events front and center in the scientific community. So what I want to do now is take a bit broader perspective, an Earth system perspective, because we need to understand that the entire planetary life support system is changing at an extraordinary rate and the implications of this. So we can start again with the IPCC. Look at this right-hand panel. This is the temperature increase from 1850 to the present. You can see from about the mid-20th century, it really accelerated. And in fact, we can measure that the rate is increasing as we go through time. Now, that doesn't look too dramatic when you look at it. It's up to about 1.2 now in the year 2022. But in fact, we need to look at a longer term perspective to see just what is involved here. So this is a 2,000-year perspective. So this goes back to the time of the Roman Empire and so on. So you see that there's natural variability in the climate system, but the temperature never varies by more than 1/10 or 2/10 of a degree, hardly noticeable. But this spike at the end, this is the human influence. And when you put it in a long time perspective, you can see just how dramatic this is. This is an extraordinary change in the Earth's climate, in fact, in the Earth system as a whole. We can make some comparisons to what's happened in the past in Earth's system. So if you look at the rate, how fast change is actually occurring. We're pouring CO2 into the atmosphere. And over the past 2 decades, that rate is about 100 times faster than the maximum rate during the last time CO2 went up. And that was when we came out of the last ice age between 20,000 and 12,000 years ago. Over the last half century, the average temperature, that's that spike I showed you, has risen at a rate about 200 times the background rate over the past 7,000 years of the Holocene, the epoch we're in now. This last statement from the geologist, I think, is really important. These current rates of CO2 and temperature change are almost unprecedented in the entire 4.5 billion year geological past. In fact, our planet is 4.5 billion years old. Only one time do we have a record of CO2 and temperature changing as fast as it is today. And that was 66 million years ago when a meteorite struck and wiped out the dinosaurs and caused a mass extinction event. Now, that was an emergency for sure in the history of the Earth system. So what we're saying here is that the current rates are unrivaled except for that event. Another piece of strong evidence that, in fact, we are in an emergency. But I want to show you now what the future might hold for us. So this is one of those temperature records from the year 0 AD all the way up to 2000. Here's that spike again I showed you at the end. But what I want to do now is show you the climate model projections out to 2100 and what they look like on a 2,000-year time frame. So these are the projections of the IPCC. These are the emission curves out to 2100. These are the curves that if we really get our act together and reduce emissions, in fact, we need to reduce them even more rapidly than these curves show. In fact, we're on track for about this red one here, which would take us to about a 3-degree temperature rise. So these are the corresponding temperature rises, 1.5, nearly 2, 2.7, 3.5, 4.3 degrees by the end of the century. So what does that look like on a long-term perspective? There's our graph, and that's what it looks like. So year 2100 is about out here. Here's the 1.5 lower Paris target, and here's the higher temperature projections. Look at that size and speed of that trajectory. That's extraordinary. That will probably even surpass what happened when the meteorite struck. So the Paris target's 1.5 to 2. Now we're sitting with a 10-year average at about 1.1. Current trajectory, if we just keep emitting like we are today with current policies, we're going to get around 3 degrees of temperature rise, and that is catastrophic. Worst case scenario, 4.5 degrees. From an Earth system perspective, this is an entirely new state of the Earth system. It's a severe challenge to even our contemporary civilization. I would actually change my wording there from possible collapse to probable collapse if we go to 4 degrees. In fact, I think even at 3 degrees, we might well see the collapse of our globalized society that we live in today. But what I want to talk about now are tipping points, because the whole point here is somewhere between 1.5 and 3. We're going to start activating tipping points. We'll activate some, I think, at 1.5 or even a bit below. By 2, 2.5, we've got a disaster on our hands. And the point is, if you do that, then the Earth system will be taken out of our control. It's going to go up to 4, 4.5 degrees, even if we get our emissions down. So this, if you like, is the point of no return that we really have to avoid at absolute all costs. And again, this is why we are now in an emergency. We're creeping up toward the bottom of this range where we could start activating tipping points. What does a tipping point mean theoretically? It means that you have a system that exists in 2 states. And we look at a state here as a cup in this ball and cup little diagram, this little cartoon. And so you can push this ball around, but it bounces back very quickly into its stable state. But as you start eroding that stable state, it actually takes more time to fall back down into its stable state. And we can actually see that today in some of the Earth system tipping points. But once you erode the resilience, stability to a certain point, it just takes a nudge and the system falls into a new state, a very different state, which becomes increasingly stable as long as we keep forcing the system. So this is the theory behind a tipping point, is that you reach a critical point of pressure and the system tips. So let's apply this then to the Earth system. There's been a lot of work now over the last decade in tipping points in the Earth system. They come basically in 3 types: big pieces of ice in Antarctica and the frozen permafrost, circulation changes in the ocean, El Nino and the North Atlantic circulation, monsoon systems and so on. Also loss of big biomes. The Amazon rainforest is a famous one. Coral reefs are another one that is very important for us here in Australia. And of course, the great northern forests are also prone to tipping points. Well, what does it look like? Here's a healthy coral reef. All you have to do is push it past its critical threshold by only a couple tenths of a degree, and this is what it looks like. So you can heat the water around it, and it's stable up to a certain point. And all it takes is a fraction of a degree, and you're going to get a mass bleaching event. As I am speaking, the Great Barrier Reef is suffering its 4th mass bleaching event in only 7 years. And that's because the temperature is going up and up and up. And that means bleaching events are occurring more frequently and they're more damaging. The boreal forest is an interesting one because you reach a critical temperature when a species called the bark beetle can conclude its life cycle in only 1 summer rather than 2. You get a massive explosion in population and it denudes the trees and loses a lot of carbon, kills the trees, and carbon goes up into the atmosphere. And that's a tipping point. You just got to get a critical temperature increase and that beetle's life cycle changes abruptly. So we can see this throughout the Earth system. Permafrost is a big issue. This is frozen soil around the North Pole. This is the North Pole. It exists mainly in Russia and some in Alaska and Canada and a bit around the edges of Greenland. It looks like this. These are our Arctic plains. A lot of them are waterlogged. A lot of them have a lot of lakes on them. But underneath the surface, down sometimes as far as 200 meters, there is frozen peat, wet soil that is very carbon rich. Now it's locked away from the atmosphere under a stable climate because it's frozen. But as the Northern Hemisphere warms, and it's warming twice the global average, permafrost is starting to melt. The real concern here is that these permafrost regions store something around 1,700 billion tons of carbon. And nearly 90% of that is perennially frozen, so it's locked away. But this amount of carbon is double the total amount of carbon in the atmosphere. So this is a huge carbon bomb that's sitting up in the northern high latitudes, and something we really have to worry about. Well, what do we know about tipping points today? These are all observations. If you look at the 9 tipping points listed here, In the top of each box is the name of the tipping point, Arctic sea ice. Now, the text underneath it is not a projection. This is what is happening today. It's observation. Greenland, ice loss accelerating. Arctic sea ice, it's reducing. Permafrost is starting to thaw. I mentioned boreal forest, pests and fires. Amazon rainforest, more frequent droughts. So we know these are happening. We don't think any of them, except perhaps Arctic sea ice, may already have reached its tipping point. But we're concerned that somewhere between 1 and 2 degrees, many of these may reach tipping points. Now, the arrows indicate that these are linked so that you can actually form a tipping cascade, like a row of dominoes. Tipping one, it tips another, it tips another. And here's how one might work. As Arctic sea ice retreats, darker ocean water is exposed. That increases the warming in the northern high latitudes. That increases the ice loss on Greenland. That's pouring fresh water onto the North Atlantic. That is slowing down the North Atlantic circulation, and that is leading to more frequent drought in Amazon. So melting ice on the North Pole is actually leading to more frequent drought in the Amazon through this cascade of tipping points. And the comment we made in this paper that we published in 2019 was, if these damaging tipping cascades can occur, and we think there's strong evidence they can, and a global tipping point cannot be ruled out, then this is an existential threat to civilization. No amount of economic cost-benefit analysis is going to help us. So I think that's about as clear a statement as we scientists can make, that if we start activating a tipping cascade, this is a true emergency. Well, since that paper was published, we started testing this with models. And lo and behold, the things we feared certainly appear in the models. So most of the interactions between these tipping points are positive. They further destabilize the Earth system. We found one which is stabilizing, and that is if you weaken the North Atlantic circulation, that slows the flow of warm water to Greenland, and that would help slow down the disintegration of Greenland. But that is actually overridden by the melting of sea ice in the Arctic. So the climate models are agreeing with our initial assessment. Cascades are real, and we really have to take every effort to avoid initiating one of them. We published a paper in 2018, something called the so-called hothouse Earth paper. And there what we did was use this little landscape cartoon, stability landscape, to try to depict how the Earth system operates. Now, most of you know that it's oscillated over the last 800,000 years between ice ages, which is this cold blue valley, and nice warm periods like the Holocene, which is perfect for humanity. But we've already pushed the Earth system out of the Holocene. The Holocene's gone. We're in the Anthropocene. We're about 1.1 to 1.2 degrees warmer. We're entering a deepening valley of heat in this landscape. And very soon, we think there's a fork in the road. And if we don't get on top of emissions, get them down rapidly, well before 2050, cap the temperature rise as close to 1.5 as we can, that'll get us to hopefully stabilized Earth. But this decade, if we can't get emissions down at least 50% this decade, we are concerned that we will go onto this ever deepening valley and across a waterfall, a cliff, whatever you want to call it, a threshold, into hothouse Earth. And once you start going down that, this is actually a point of no return. And this tipping cascade I talked about actually is what we visualize here as a threshold or a waterfall or a cliff, whatever you have. Well, the IPCC has assessed over the years the likelihood of tipping some of these tipping points. Notice how, as the science goes forward, this bar here on the right concerns tipping points. So back in 2001, we thought we were safe up to 3.5, even 4 degrees. By 2014, we're already into a moderate risk at 1.5, and above 2.5, we're going to a moderate to high risk. And in 2019, it's even worse. So basically, the IPCC is agreeing with us that the risk of these tipping points is already significant at 1.5. It's pretty bad at 2, and anything above 2 is extremely dangerous territory. So as our knowledge improves, tipping elements appear to be vulnerable at lower temperatures. So this is an important message that I think you need to put forward, is as the science improves, the future looks much riskier at lower temperature increases. And this is really solid scientific evidence for the fact that we are actually in a climate emergency in 2022. In fact, we have been for a few years now. So if you look at the projected temperature rise from the IPCC, by 2050, middle of the century, 30 years out, even under the most drastic emission reduction scenario they assessed, we'll still hit 1.6. This is dangerous territory. As I said before, we're on track to reach somewhere around 2.7 or 3 by the end of the century. But these other scenarios will reach 2 or breach 2 even by 2050. So even the IPCC is saying we're entering dangerous territory unless we do something really drastic. So it's virtually certain that we will breach 1.5 before the middle of the century. Some people think even by 2035 we could reach 1.5. Now here's a good way to define the climate emergency. It's using an engineering approach. So if anyone wants to challenge you about whether we're in a climate emergency, this is good, solid, quantitative evidence that we are. And it involves two concepts: intervention time and reaction time. So what do I mean by this? The reaction time is the time it takes for us to get to net zero emissions and start stabilizing the climate. Let's take the IPCC assessment and say the best we can do is 2050. Now that's not good enough, but let's just take this because a lot of people, a lot of countries are saying net zero by 2050. All right, that's a reaction time of 30 years. Actually, now it's 28 years. But what are the intervention times to stop tipping points? Okay, Arctic sea ice. I think we're right at it now. I think it's 0. I think within this decade that's going to tip, and I think by 2040 or 2050 you'll see an ice-free Arctic Sea. West Antarctic ice sheet, about 3 meters of sea level rise. I think within 10 years that's going to go over its tipping point, and we'll be committed to losing it. Amazon forest, I estimated 15 years. A good colleague of mine, Carlos Nobre, who's an expert, said that's optimistic. He says the tipping point will be reached in 5 to 10 years. He's the world's expert on that. That's not only a climate issue, that's a huge biodiversity issue if that thing tips, and it's likely that it will. And even the Greenland ice sheet, 7 meters of sea level rise, tipping point, 20 to 25 years. And if these all tip, a cascade is very likely. So this is telling us that if we're talking about net zero by 2050 is too slow, that is not sufficient to stop a tipping cascade. And this is pretty solid evidence that this is what we're facing. And it really raises the question, are we already losing control of the system? Now, the other way to look at the climate emergency is this. These are the observed emissions in billion tons of CO2 from 1850 to the present. Notice that this follows a very, very good mathematical curve. It's an exponential growth curve, growing by 1.65% per year. And of course, that's really, really, really bad news. But notice that all the science we put in, estimates of climate sensitivity, IPCC first assessment, sixth assessment, and so on, we have had no impact whatsoever on the emission reduction curve. Worse yet, look at the governance, the policies. You have Kyoto Protocol, Paris Agreement, absolutely no impact. So this is a pretty good summary. We just had the COP26 meeting. A lot of people are saying, wasn't that great? We came out of Glasgow with a lot of good things. No, it failed. And everyone before it has failed. And now we're saying, well, COP27, if we keep going the way we're going, it's futile. So the point I'm trying to make is that all the science in the world, all the COP meetings in the world, we have not begun to bend this curve at all. The only things that affect it are things like COVID and economic downturns. And that has nothing to do with policy. So here's the emergency. If you want to have any hope of stabilizing the climate between 1.5 and 2, we've got to get emissions cut in half by 2030. So we're up about 40 now, half is 20, 2030 is there. Look at the shape of that red arrow. And if you don't think that's not an emergency situation to meet that, I'm not sure what you're thinking or what you're smoking, because this is an absolute emergency. Already, we had the chance to come out of COVID. We dropped emissions in 2020 with COVID by about 4.5 or 5%. Did we use this opportunity? No. in 2021, they rebounded nearly to pre-COVID levels in 1 year. So this is another really solid piece of evidence that we are, in fact, in a climate emergency. Well, that's the science. We're doing our best as scientists to try to get this point across. The students, the next generation, are probably the more effective ones in getting the message across. This is my favorite photo taken in front of the Australian Parliament House, where the students here have this lovely connection to Greta Thunberg and the Swedes, and this tongue-in-cheek comment about our present government. Anyway, I'm going to stop there because Nick has more to say. But if you have any questions about my analysis on a scientific basis of why we are now in a climate emergency, it's not going to be an emergency in 5 years.